Right now, a machine invented in 1884 is generating more electricity than all the world's wind farms and solar panels combined. Before we get into the mechanism, the scale of this needs to be precise. Every coal plant, steam turbine. Every nuclear plant, steam turbine. Every concentrated solar plant, steam turbine. Most geothermal plants, steam turbine. The back half of every combined cycle gas plant, steam turbine. The figure most often cited for the steam turbines is around 40%. That number counts only coal and nuclear. When you include the steam section of combined cycle gas plants, geothermal, biomass, and concentrated solar, the IEA's 2024 data puts the steam turbine involvement above 55% of global generation. The headline figure understates the case. Wind and solar combined sit at roughly 14%. The machine from 1884 is not a rounding error. It is the backbone of the grid. The reason is not inertia, it's physics. And that's what we're going to work through. Strip away every complication, and a steam turbine is doing one thing, converting the energy stored in high pressure, high temperature steam into shaft rotation. That shaft drives a generator. The generator produces electricity. That's the entire chain. The efficiency of that energy conversion, steam to electricity, runs between 85 and 92% in a modern machine. That number is almost impossible to beat with any other technology at this scale. It's the core reason this machine has dominated for 140 years. The thermodynamic cycle is called the Rankine cycle. 4 stages. Each one matters. Water enters a boiler and is heated under high pressure. At around 550 to 600 degrees Celsius and 160 to 300 bar, it becomes superheated steam. Not wet, not saturated, but dry gas with enormous stored energy. That superheated steam carries roughly 3,500 kilojoules per kilogram. The steam is then condensed back to water, cooled by river water, seawater, or a cooling tower. And the cycle repeats. The pressure ratio is the key number. You're going from 160 bar at the turbine inlet to 0.05 bar at the exhaust. That 3,200 to 1 ratio is what makes the energy extraction so complete. The lower the condenser pressure, the more work you extract. This is why the condenser is as important as the turbine itself. The turbine is not a single set of blades. It's a series of stages across 3 sections: high pressure, intermediate pressure, and low pressure. Steam enters the HP section first, small, tight blades under high pressure. It does work, loses energy, expands, moves to the IP section, more work, more expansion. Then the LP section, much larger blades because the steam volume has increased enormously. Here's a number that surprises most people. The steam entering the high pressure section occupies about 0.02 cubic meters per kilogram. By the time it exits the low pressure section, it occupies nearly 20 cubic meters per kilogram, 1,000 times its original volume. Within each stage, the fixed stator vanes accelerate the steam and direct it at a precise angle onto the rotating blades. The blades are aerofoils. Steam acts on them by pressure differential, exactly the same principle as a wing generating lift. The shaft rotates at 3,000 revolutions per minute in a 50 Hz grid, 3,600 in a 60 Hz grid, locked to the grid frequency. In a real 500 megawatt unit, the kind that powers roughly 400,000 homes, here's what that cycle looks like end to end. The boiler burns fuel at around 1,400 degrees Celsius. Superheater tubes in the flue gas path raise steam to 565 degrees Celsius at the turbine inlet. Most modern plants add a reheater. After the HP turbine, steam returns to the boiler, is reheated, then drives the IP turbine. That single reheating step adds roughly 5 efficiency points. On a 500 megawatt unit, that's 25 megawatts of additional output from the same fuel. The turbine hall is one of the most demanding environments in mechanical engineering. The HP, IP, and LP casings sit on a single shaft, sometimes 30 meters long, rotating at 3,000 revolutions per minute, within radial clearances of less than half a millimeter. The condenser sits directly below the LP turbine. Keeping the exhaust at near vacuum, 0.05 bar, is what closes the thermodynamic loop. Let's talk about how this system fails, because failures reveal what nominal operation conceals. The LP turbine blades are the most mechanically stressed components in any thermal plant. 2 meters long, up to 100 kilograms each, spinning at 3,000 revolutions per minute. The centrifugal force at the tip of a large LP blade is approximately 50,000 times gravity. The dominant failure mode is high cycle fatigue. LP blades undergo roughly 1 billion stress cycles per year. A microscopic crack, initiated at a surface pit from wet steam erosion, a machining mark, or a weld flaw, propagates incrementally under each cycle. This is not a theoretical failure mode. In 1997, the U.S. Nuclear Regulatory Commission issued Information Notice 97-19, documenting a pattern of LP turbine blade separations across multiple operating nuclear plants. So why can't we just replace all of this with wind and solar? The honest engineering answer has three parts. First, capacity factor. A 500 megawatt wind farm generates its nameplate power about 35% of the time. Solar, about 22%. A steam turbine runs at 85 to 92%, continuously on demand. Second, synchronous inertia. Every spinning turbine rotor is a physical flywheel connected to the grid. When demand spikes suddenly, the rotational energy in those rotors instantaneously resists the frequency drop. Wind turbines and solar panels connect through power electronics. They provide no synchronous inertia by default. Third, dispatchability. A steam turbine can be called to any output level on a schedule. The fuel is stored on site. At 2025 prices, grid-scale battery storage equivalent to 1 day's output from a single 500 megawatt plant costs roughly 20 to 30 times the turbine capital cost. Here's where this gets genuinely interesting. The steam turbine is not a static. It's being transformed, not replaced, transformed by three technology shifts happening right now. The first is ultra-supercritical steam conditions. Ultra-supercritical plants reach 47 to 49% thermal efficiency. The second shift moves away from water entirely to supercritical CO2. A 10 megawatt SCO2 turbine fits on a workbench. The third transformation is in operations. Every major OEM now runs digital twin platforms. A digital twin predicts failure weeks before any physical symptom is detectable. Three things to take away. 1. Steam turbines dominate global electricity not because of inertia, but because the Rankine cycle and rotating machinery deliver shaft-to-wire efficiency that no current grid-scale alternative can match. 2. The barriers to replacement, capacity factor, synchronous inertia, dispatchability, are quantifiable engineering constraints. 3. The technology is actively evolving. Ultra-supercritical steam, SCO, 2 cycles, and digital twin operations are changing what this machine can do. The logical next video is combined cycle gas plants. If you work in the industry and there's something here I got wrong or missed, the comments are there. Subscribe if you want the next one when it's ready.